Okay, this is our next topic. I'm going to introduce ANOVA. So, we've been talking about situations in which we compare two groups or treatments or conditions, two means, and we're interested in the null hypothesis is generally is the mean of one population is equal to the mean of another population. But what if we have an experiment in which we have more than two means, more than two groups, more than two conditions? In this case, we're going to have to figure out what to do. So let's say we have a study in which we conduct, in which we're interested in comparing the effects of three drugs on depression. We have Prozac, Zoloft, and Elavil, and these are all real drugs and so on. And we want to compare them against a placebo condition, a condition in which people get a pill, but it just contains sugar, a control condition. So we select 24 people and we randomly assign them blindly to one of four conditions. Either they receive Prozac, Zoloft, Elavil, or placebo. The colors of the pills are all the same, but what's contained in the pills differs. What the medicine in the pills differs, but the participants in the study don't know what they're receiving. That's why we call this blindly. We don't tell them what they're receiving. We tell them that they're going to get a blue pill and all the pills are blue. What's different is the medicine in the pills, and only we know what medicine is in the pill. So we say that that's a blind study because the participants don't know what treatment condition they are in. This goes to the reason we blindly assign people to um, conditions is that we don't want their expectations to affect the outcomes. We don't want them to um, be sort of happy that they got in one condition versus the other. After 1 month of drug therapy, we measure depression, and here are the scores. Now, what are we going to do? It turns out that embedded in this design, we could compare Prozac versus Zoloft, but we could also compare the Prozac versus the Elavil. We could compare the Prozac versus placebo. We could also compare Zoloft versus Elavil and Zoloft versus placebo, or placebo versus Elavil. There are in this six pairwise, we call them, comparisons, six pairwise comparisons. And that's an important term that's used in statistics. And in a four group design, it turns out you have 4 minus 1 to the factorial, 4 minus 1 factorial possible comparisons, or 3 times 2 times 1 comparisons, or six comparisons. So could we do six separate t-tests? I mean, that's what we got. Well, it turns out that we can't, and we can't because of probability theory. Making a correct decision when the null is true is generally speaking 1 minus alpha. In my lecture on errors in hypothesis testing, one type of correct decision is failing to reject the null when it's true. And the probability of that is 0.95. So when the null is true, the probability of failing to reject it is 0.95. So that's a correct decision. Now, if we assume that each test is independent, then the probability of making the correct decision across all six tests when the null is true is the product of those probabilities, meaning it's the probability of making the correct decision in the first comparison times the probability of making a correct decision in the second times the third times the fourth. It winds up the probability is no longer 0.95 across six comparisons, but 0.735. Thus, the probability of a type 1 error is not alpha, but is 1 minus the probability of making a correct decision. Or in this case, it gets elevated. We increase alpha inadvertently to 0.265. And it turns out the problem is this assumption right here, this assumption that each test is independent. They are not independent because the data that we're using to compare Prozac versus Zoloft is the same data that we're using to compare Prozac versus placebo. These two comparisons are not independent. These two comparisons are not independent because we're using the same data from the Prozac condition. This sample of treatment outcomes following Prozac is just one possible sample. And it's a good sample, but it's not necessarily a perfect sample. It's got some problems in it. And by using it in multiple comparisons, we exacerbate the problems contained in the sample by using it two or three times. The same goes for Zoloft, which we use 3 times. That same sample, the same data from the Zoloft condition we're using in 3 comparisons, but it's not a perfect sample. It's got some problems in it. We can deal with this, a random distribution of problems, but these are no longer random anymore when we use them 3 times. The same goes for Elavil, the same goes for placebo. That's why this problem is exacerbated. It's compounded across multiple comparisons. So we cannot do multiple t-tests without doing something else. It just elevates our type 1 error. So let's go back and look at a t-test, a t-statistic. In the end of the last, a couple of lectures ago, I told you that, boy, it looks like the t-statistic is this ratio. Our numerator is an obtained difference, that is the difference between the means of the 2 samples. In the independent sample t-test, it's just the difference between the means. In the dependent sample t-test, it's the mean difference. Those wind up being the same. Then we put it over this error term, we call it. And this we could call the difference expected by chance. So it's these 2 differences. It's one is the difference that we expect, one is the difference that we get. Now, in the denominator, in the t-test, this is pooled variance. We take all the variances and we put them together. Now, if we have 4 groups, we can just put all the variances from the 4 groups together. We just need a bigger pool, right? As I've said, pooled variance in the t-test was putting 2 variances together. Well, why can't we put 3 together, or 4, or 5? If we have 4 groups, let's put all the variances together. Now, the top term, a little bit more trouble. In the t-test, we calculate them as differences between the obtained means or the mean difference. Is there some way to subtract multiple means from one another? Do we take the first mean and subtract the second, subtract the third, subtract the fourth? What do we expect to happen? Well, we'll probably get a big negative number because these will, subtracting 3 means from 1. Then do we subtract the first, second, and third from the fourth? There doesn't seem to be any order or any reliability or any systematicity to this sort of thinking. But we can ask ourselves, is there a statistic that quantifies how scores differ from one another? In other words, what statistic describes how scores differ from one another? And the answer is variance. Variance is a measure of how the scores differ from one another in a set of scores or in a distribution. So what if we were to look at the variance between means? What if we were to treat the means as scores and calculate the difference between the means, the variance between the means? That would be interesting. So, in a sense, what we're going to do is reconstruct the t-statistic as a ratio between variances. The variance between means divided by pooled variance. But a t isn't a ratio of variances. A ratio of variances is an F statistic. We know that if you take one variance divided by another variance, you wind up with an F statistic, and it will be distributed as an F. The same distribution that Ronald Fisher discovered and described. So what we're going to do is we're going to take pooled variance, and unfortunately we're going to start using different names. We're going to start using the name mean square error or mean square within for our pooled variance term, or a within groups variance estimate, and our mean square treatment or mean square between, which is our variance between means, we're now going to call mean square between. The term mean square is equivalent to the term variance. So analysis of variance, or ANOVA, allows us to compare multiple group means without compromising alpha. And even though an analysis of variance uses variances and the F statistic, it helps test hypotheses about means. Between groups variance is a measure of the variability obtained between the groups. How much do the groups differ? We answer that question with our between groups variance estimate. Within groups variance estimate is our measure of how much they would differ by chance. And this ratio is going to be distributed as an F, and we're going to be able to test hypotheses about it. All right, we'll move on to some more discussion about how we do ANOVA in the next few videos.